Hey guys, welcome to today's class. Have fun.
Okay, today we'll be looking at the topic stoichiometry, mass and volume relationships, mole ratios, mole concepts, and basically calculations that has to do with reactions of chemical elements. I'm talking about stoichiometry. Stoichiometry basically is the art of measuring chemical elements in quantitative relationship in chemical reactions. Talking about stoichiometry, now the principal three key things here. Now we're talking about measurements, we're talking about quantitative relationships and chemical reactions. So basically, stoichiometry has to do with chemical reactions. Now you have A plus B gives us C. You have two reactants A and B combined to give us a product C. Now, the art of measuring these chemical elements. Now, the chemical elements in this case now is A and B, and the new compound formed C. Now, the art of measuring chemical elements in quantitative relationship. Now, in the aspect of quantitative now, we are talking about quantity of the entities now. Quantity in the sense that you can be talking about the number of moles, you can be talking about number of moles, you can be talking about their mass, you can be talking about the volume, you can be talking about the molar mass, you can be talking about their concentration, and so on and so forth. So quantity in the sense that we're talking about the numerical extent to which these elements occur in various forms of chemical reactions. So, and finally, in chemical reactions, of course, reactions occur between elements, various types of reaction. So, stoichiometry is the art of measuring chemical elements in quantitative relationship in chemical reactions. So, basically, stoichiometry is like the mathematics of chemical equations. So I put it as the mathematics of chemical reactions. So you have experiments, different types of reactions between elements occurring in the periodic table. So the analysis of the quantities of the elements, I've explained number of moles, mass, and so on and so forth. So the relationship that exists between these elements and their quantities is what we refer to as stoichiometry. Now, simple or examples of reactions now in which the study of stoichiometry is used to explain. We have precipitation reactions, we have displacement reactions, we have synthesis reactions, and reduction reactions. Now, like I said earlier, stoichiometry is like the mathematics of chemistry. So basically, we are going to be solving at most 20 questions now on this topic. And because the topic is not much into the notes like definitions, instead we are going to the analysis of chemical reactions to see how this quantitative aspect of the reaction affects the chemical elements. So a quick example now before we start looking at calculations, we need to understand some simple reactions in which we can use the knowledge of stoichiometry to analyze. So one example of a chemical reaction here now is a precipitation reaction. Now I'm talking about a precipitation reaction. You're simply talking about the formation of precipitates. Now a precipitate occurs in some type of chemical reactions in which some there is a displacement of probably particular elements or compounds or ions of the elements. You have you have a kind of solid like, or you have a kind of, you notice a change in states of the reaction. Example, you have a reaction given here, and you have barium chloride. Now barium chloride is aqueous it is in the liquid form, it is in a solution. Now, you have potassium tetraoxochromate 6. It's also in its aqueous state. Now, on the combination of these two compounds together to give us barium CrO4, that is to give us barium tetraoxochromate 6 and potassium chloride. It is noticed that KCl also came out as aqueous, but this came out as a solid now. So a precipitate is most likely a solid which comes out or which precipitates out of a chemical reaction. So now you have a liquid and a liquid combining, and during the course of the experiment you have precipitates. Now you can have a white precipitate, you have a red precipitate at the surface of the reaction chamber. So using the knowledge of stoichiometry now, you can be able to calculate the amount of the precipitate, in short form precipitate, which was released during the course of the reaction. So, and these calculations now can only come to play as a result of the knowledge of stoichiometry. In which case you have to study the amounts of reactants that occurred in the reaction, their concentration, the number of moles, the volume, to be able to calculate the amount of these precipitates which came out of this reaction. So this is as a result of the knowledge of stoichiometry. So also we have displacement reactions. So we have displacement reactions. Now talking about displacement reactions, another example here we have a reaction between magnesium solid, hydrochloric acid, to give us magnesium chloride and hydrogen gas. Now, magnesium solid came into the reaction. Magnesium came into the reaction as a solid to combine with aqueous solution of hydrogen chloride, hydrochloric acid. Now, during the form of the reaction, magnesium displaces hydrogen to combine with chlorine to form magnesium chloride. Now, hydrogen gas is being evolved from the mixture. So the amount of hydrogen gas which was displaced in this reaction can also be calculated as a result of the knowledge of stoichiometry. So stoichiometry is very important. It's a very important aspect of chemistry because of reactions occurs during chemical combinations and reactions. So also we have synthesis reactions and we have reduction reactions. So talking about reduction reactions, we know what redox reactions are because during the course of this course, chemistry, past topics have been treated on redox reaction, redox and oxidation. You have the gaining and losing of electrons, mixing with water, gaining oxygen, losing oxygen, and so on and so forth. So basically all reactions in chemistry need to be mathematically calculated to know the amount of reacting elements and products formed, the relationship between the mass and volume, and so on and so forth. So quickly now, before we start calculations now, we'll be looking at some important parameters which we are going to be using. Okay, now since I said stoichiometry involves quantitative relationship in chemical reactions, now you have some parameters to find quantities. Now you have some parameters which you are going to be making use of. Now you have the mass. The mass is represented as small letter m. It is in gram or kilogram. You have the molar mass, capital M. So the molar mass is in grams per mole. Now this can either be in grams or can be in kilogram. To convert grams to kilogram, 1000 grams is equals to 1 kg. So we have molar mass, the molar mass of an element, or the molar mass of a compound from the previous classes also, which I explained to us the relative atomic mass, relative molecular masses for elements, for compounds, combination of elements. We have volume. Now, our volume can be in centimeter cube. It can also be in dm cube. And we have the molar volume, V subscript m. So our molar volume is in dm cube. And we have our amount, the amount of substance, the amount of the elements, the number. We have N, which is in mole. We have molar concentration, which is in C, which is mole per dm cube. And we have mass concentration, P, which is gram per mole. Also, we have Avogadro's constant, which is in per mole. So these parameters are what we are going to be using. So the simple combination of these parameters now is what we'll be looking at in order for us to be able to solve stoichiometry, in order for us to understand the use of stoichiometry to solve chemical equations. Now we have this formula. These are just arrangement of the parameters. So you have the molar mass now, or this is just an interchange. So first, if I'm using this now, our number of moles is equals to mass over molar mass. So what this simply tells us is that to find our number of moles, we just say the reacting mass over the molar mass. So and we know what the molar mass is. The molar mass is the mass of 1 mole of that compound, or the mass of 1 mole of that element. So we have our Avogadro's constant, which is equals to N over A. We have molar volume equals to V over N. Interchanging this now, I have another simplification of the formula. So the first formula which I want us to know is this, that our number of moles is equals to reacting mass over molar mass. So you have hydrogen now, for instance. Now the molar mass of hydrogen has a molar mass of 1.00 gram per mole. So 1 mole of hydrogen gas is 1 gram. So for hydrogen gas, which is H2, so the mass of H2 will be 2.00 grams per mole. So the units for our molar masses is in grams per mole, because molar mass now is the mass of 1 mole of that element. So 1 mole of hydrogen, so the mass which is in gram per mole. So this is the unit for our molar mass, M. While this is just the mass, maybe 2 grams of 5 kg of hydrogen was reacting in the experiment, in the reaction. So that's just the reacting mass. Also, we have number of moles can be the volume, the given volume at STP over our molar volume. Now, for every mole of a gas at STP, that is standard temperature and pressure. Now, the standard temperature is 273 Kelvin, and the standard pressure is 1 atmospheric pressure, 1 atm. So, for every mole of a gas at STP, the volume is always 22.4 dm cube. So we should note that all these formulas, I want us to be noting them, using them when solving. So I'll just be referring us back to them. Now we have C. C is the concentration. Now concentration is equals to N over V. N is the number of moles. Now over volume, C. So when you say concentration now, concentration is N over V. And we know our number of mole, N is the number of moles is in moles, and volume is in dm cube. So the unit for C is mole per dm cube. So these are simple ways of analyzing them. So also we have molar concentration. Now the formula for molar concentration is our mass concentration all over the molar mass. So our molar concentration, which is in mole per dm cube, is equals to mass concentration, which is gram per dm cube, all over our volume, which is in our molar mass, which is gram per mole. Now you can see on simplifying this now, grams cancel gram, and simplify this gives us mole per dm cube. So our molar concentration, which is C concentration, is equals to the mass concentration over the molar mass. So it's something quite similar to this. Your number of moles is mass over molar mass, but here molar concentration, just have concentration added to this and this. So the molar concentration equals to the mass concentration over the molar mass. So this which is in mole per dm cube. This is in gram per dm cube, and this molar mass is in gram per mole. Okay, so we have conversion. Okay, because I said we'll be using dm cube or cm cube now for our volume. So to just switch to convert, okay, because 1 dm is 10 centimeter. From 10 millimeters make 1 centimeter. 10 centimeter makes 1 decimeter. So 1 decimeter is equal to 10 centimeter, and 1 decimeter cube is equal to 10 raised to power 3 centimeter cube. So that's because 1 dm equals to 10 centimeter. So 1 times 1 times 1 dm will give us 10 times 10 times 10 cm cube. So to convert 1 dm cube to centimeter cube, it gives us 10 raised to power 3. That's 10,000 centimeters cube. So quickly, I want us to run through the formulas again, which we make use of. Okay, you also have this formula here. This formula is used for converting our volume, for finding our volume now. So if you are given a question which involves gases, now I said we are talking about mass volume relationships and mole. So for the reactions that involve gases, gases combine in mole or volume. You have so volume of hydrogen gas react to so volume of oxygen gas. So for gases now, we are talking about the volumes, reaction with respect to volumes. So to find the volume of that gas, you have the initial pressure of the gas, the initial volume of the gas, the initial temperature multiplied by T2 over P2. Now 273, which is the standard temperature, 760 millimeters mercury milliliters bar is the standard pressure. Now it told us our standard temperature is 273 Kelvin or 1 atm. Now 1 atm is equals to 760 mmHg. So this is what we'll be working with. So to find our V2 gives us P1. Now this is coined from the general gas laws now. Talking about gas laws, Boyle's law, Charles' law, combination of them. Okay. So for a given volume of a gas at an initial pressure and temperature, the volume of that same gas at STP will give us this using this formula. Now because I've told us that 1 mole of a gas at standard temperature and pressure is this. So if you are given a gas which is not at STP, but you want to find the mole of the gas at STP, you have to convert the gas from its initial volume, pressure and temperature to the standard temperature and pressure. So we'll be looking at 1 mole. What is a mole? We all know 1 mole of a substance is the amount containing as many elementary entities as the number of atoms in exactly 12 grams of carbon-12. I've explained this in previous classes, which I will implore us to check on the YouTube channel. So a mole of a substance is simply the amount containing as many entities as the number of atoms in exactly 12 grams of carbon-12. Now, carbon-12 is the reference element now. So when you say 1 mole of a substance, 1 mole of hydrogen gas, 1 mole of carbon, 1 mole of ammonia, 1 mole, and so on and so forth. So you're talking about the number of atoms or the number of entities in that element. So we'll be looking at mole ratio now. And for mole ratio, the mole ratio in which reactants combine and products are formed gives the stoichiometry of the reaction. This is the part I explained earlier on. You have reactants and products. The ratio in which the reactants combine and products are formed gives us the stoichiometry, because the stoichiometry talks about the quantitative relationship. So if I have 1 mole of A combined with 2 mole of B to give me 3 mole of C. Now the relationship between them, which is 1:2 to give me 3, is what we refer to as the mole ratio. And the mole is always a coefficient of the elements. So you can have, say, calcium, see 3 at the front. Now 3 signifies the number of mole. You can have 2HCl. Now 2 signifies 2 moles of HCl. So quickly now, okay, you have amount times molar mass is equals to reacting mass. And this is what I explained earlier on. I told us N equals to M, capital M. Amount N times molar mass would give us the reacting mass M. So this is just a change of subject of the formula. So now we'll be looking at examples, 20 past questions now, WAEC past questions. So these are the formulas we should be making use of very quickly now. Number of moles is equals to mass over molar mass. Number of moles is equals to the volume at STP over the molar volume. 1 mole of a gas at STP is 22.4 dm cube. Our concentration is equals to number of moles over volume. V2 is equals to this. Molar concentration is equals to mass concentration over molar mass. So I'll employ us to be familiarized with the units as well, which will be using mass as in gram or kilogram, molar mass gram per mole, volume is in cm cube or dm cube, molar volume dm cube, amount is in mole, the molar concentration, mole per dm cube. Mass concentration should be grams per dm cube, sorry, this is grams per dm cube. Talking about concentration, talking about volume. Okay, so I have my first question we're solving today. This is a NECO 2019 past question. This is the objective parts of the question, question 32. And it says, calculate the number of moles of calcium chloride that can be obtained from 20 grams of limestone in the presence of excess hydrochloric acid. And this is limestone, calcium trioxocarbonate 5, and plus 2 HCl. HCl, that's hydrochloric acid. It combines to give us calcium chloride, water, and carbon dioxide. And these are the reactants, these are the products. Now you have to find the number of moles of calcium chloride that can be obtained from 20 grams of limestone. So this is our chemical reaction. It gave us CaCl2 plus H2O plus CO2. This is solid, aqueous, liquid, and a gas. So these two are our reactants. Now our mole ratio is what? 1:3. No, sorry, 1:2. 1 mole of this combines with 2 moles of this to give us 1 mole of calcium chloride, 1 mole of water, and 1 mole of carbon dioxide. So firstly, we write out our mole ratios. This is the mole ratio. And we are told that what number of moles of calcium chloride will be obtained from 20 grams of limestone. Good. So the first thing now, we've interpreted our mole ratios. Now we are asked to find the amount of CaCl2 which will be gotten from limestone. So first now we need to find the relative molecular mass of limestone. And the relative molecular mass of limestone, now recall we are given their respective atomic masses. Calcium is 40, carbon is 12, oxygen is 16, and so on and so forth. So using that now to find the relative molecular mass of of limestone now. So calcium has a mass of 40, carbon is 12, and oxygen, you have 3 molecules of oxygen, 3 into 16. So this gives us 100 gram. So 1 mole of limestone is 100 gram per mole. So we should note that. So 1 mole of limestone is what? 100 gram per mole. So which means that, so for CaCl2 now, calcium chloride, also we find the relative molecular mass. So and calcium, that's 40 plus 2 atoms or 2 moles or 2 atoms of chlorine, that's 2 into 35.5. This gives us 111 gram per mole. So what does this imply is that 1 mole of limestone gave us 1 mole of calcium chloride. 1 mole of limestone gave us 1 mole of calcium chloride. So now we are told how many moles of calcium chloride now will be formed from 20 grams of this. So for 20 gram, we need to find the number of moles that 20 gram contain. 1 mole contains 100 gram. How many mole will 20 gram contain? Now using the formula N equals to M over molar mass now. So we are told for 20 gram, that's the reacting mass. And the molar mass of the limestone is 100 grams per mole. 100 grams per mole. So our N is equals to 0.2 mole. So if 1 mole of limestone produce 1 mole of calcium chloride, 20 gram of limestone, which is 0.2 mole, would also produce 0.2 mole. So 20 gram is 0.2 mole, would also produce this. So our answer here is 0.2 mole. So which is this. So you can see how the study of how stoichiometry helps us to analyze this chemical reaction. You have a reaction, you find the mole ratio, you equate them, you calculate the relationship between the quantitative properties, the mass, the number of moles, and so on and so forth. So we progress now. So I have another question still on the same NECOPASS question. So it says calculate the mass in grams of 4 moles of oxygen gas. The mass in grams of 4 moles of oxygen gas. Now what is oxygen gas? O2 is oxygen gas. Now the relative molecular mass of oxygen gas gives us 2 multiplied by the RAM, the relative atomic mass of oxygen is 16. We're given 16. So 2 times 16 gives us 32 gram per mole. Okay, so which means that 1 mole of oxygen gas is equals to 32 gram per mole. Now I said find the mass in grams of 4 moles of oxygen gas. So if 1 mole gives us 32 gram, 4 moles of oxygen gas will give us how many? So there are 2 ways to it now. We can use the relationship N equals to M over M to give us, since we know the number of moles now, 4 is equals to M, don't know, over the molar mass of oxygen gas is 32. So M is equals to 32 times 4, and that gives us 128 gram per mole. Or we can simply say if 1 mole of oxygen is 32, 4 mole will be dash and we just cross multiply. 4 times 32 gives us 128 also. So 1 mole of oxygen gas is 32 gram per mole. 4 moles of oxygen gas is 128 grams per mole. So I have another question here. I'm still on stoichiometry because we are dealing with volume, mass, number of moles, relationships. So here we said, what is the percentage by mass of sodium in sodium trioxocarbonate 4 decahydrates? We are given the relative atomic masses of the elements. And what is the percentage by mass of sodium in that compound? Now, sodium trioxocarbonate 4 decahydrates, that's Na2CO3, decahydrates, and this is the compound. So we are asked to find the percentage by mass of sodium. Now, what is the percentage of sodium in this compound? What is the percentage composition of sodium? First, we need to find the relative molecular mass of the compound. And to find that, okay, we have sodium, 2 atoms of sodium, 2 into 23. And remember, we are given the atomic masses, so I'm just slotting them, plus 12 plus 3 atoms of oxygen, 3 times 16, plus 10 H2. What is the relative molecular mass of H2? For hydrogen, 2 into 1. For oxygen, which is 16. So this gives us 2 times 23 plus 12 plus this. And then solving this, we have 286 grams per mole. So this tells us that 1 mole of sodium trioxocarbonate 4 decahydrates is 286 grams per mole. And that tells us what is the percentage by mass of sodium. Now in this compound, you can see that this is sodium now. Now what is the mass of sodium in this combination? That's just 2 times 23. 2 times 23 gives us 46 grams per mole. So the percentage by mass of sodium in that composition, that's simply 46 over 286 times 100%. And that gives us 16.1%. So that's 16.1%. Okay, so we have another objective question there. It says, how many moles of potassium heptaoxomanganate 4 are in 200 cm cube of 0.105 moles per dm cube of a solution? Okay, it says how many moles of K So it says how many moles of potassium heptaoxomanganate 7, are in 200 centimeter cube of 0.105 moles per dm cube of the solution. Okay, now I said how many moles. Let's find the number of moles now. Are in 200 cm cube, and that is a volume, 200 cm cube of 0.105 moles per dm cube of the solution. That is the concentration. Remember that concentration is in moles per dm cube. So we are given the concentration of the solution. This is the concentration of the solution. So we have to find the number of moles here, a certain volume, and the concentration. Now, if you recall from one of the formulas which I gave earlier, that concentration is equals to number of moles divided by the volume. So we have the concentration in moles per dm cube, but our volume is in centimeter cube. So we have to convert centimeter cube to dm cube. And if you recall that 1 dm cube equals to 10 raised to power 3 centimeter cube. So how many dm cube will give us 200 cm cube? So that will just be saying 200 over 1000. Give us 0.2 dm cube. So now we can come back to our formula. So to find the number of moles, N is equals to CV, and our concentration is 0.105. Our volume is 0.2. So multiplying this gives us 0.021 mole. So the number of moles of potassium tetraoxo manganate 7 in this certain volume of concentration is 0.021. So that's 0.021. So up next now we have the theory question, and one of the theory questions of the same examination question. I'll be solving 2AII. And it says calculate the number of oxygen molecules required to convert 7.5 dm³ of sulfur 4 oxide measured at STP to sulfur 6 oxide. Now you have to find the number of oxygen molecules which will be required to convert a certain volume of this to give us this at STP. And we're given molar volume of gas to be 22.4 dm³. We're given Avogadro's number to be 6.02 times 10 raised to power 23. So you have to interpret the parameters which we are given. So we are told, okay, so this is the chemical reaction equation we are given, which I've written here. So this is our mole ratio. 2 moles of this combined with 1 mole of oxygen to give us 2 mole of sulfur 6 oxide. So, but now we're told to calculate the number of oxygen molecules required to convert 7.5 dm³. Now, in the first instance, 1 mole of oxygen and 1 mole of oxygen molecules would give us 2 moles of sulfur trioxide. This. Well, now we are told the number of oxygen molecule required to convert just 7.5 dm³ of this. So 1 mole of oxygen combines with 2 mole of SO2 gas to give us 2 moles of this product now. But now, since we are told now that 7.5 dm³ of this is what is reacting now, so we have to find the number of moles of 7.5 dm³ of sulfur 4 oxide gas. So recall one of the formulas which I gave us, that N is equals to V over molar volume. So the volume we were given here was 7.5 dm³, 7.50 dm³. Now I told us our molar volume is 22.4 dm³. So 1 mole of any gas at STP is 22.4 dm³. So we have to find measured at STP. So the molar volume is 22.4. So the number of moles of sulfur 4 oxide gas at STP is 0.33 mole. So since 2 moles of SO2 gave us 2 moles of SO3 by combining with 1 mole of oxygen gas, so that means 2 mole of SO2 reacts with what? 1 mole of oxygen gas. But now in this case, since we are given the volume, so in this case now 0.33 mole of SO2 reacts with what mole of oxygen now? Now the mole ratio gave us 2 moles react with 1 mole, but we are given a certain volume of the gas now. So to find the number of moles, you divide by molar volume. So the reacting number of moles now become 0.33 mole. So if 2 combines with 1 to give us this, now what mole of oxygen will combine with 0.33 mole of sulfur 4 oxide to give us the same product? So by writing this out, 2 moles of sulfur 4 oxide give us plus react with 1 mole to give us this. So we're now told 7.5 dm³, we've converted N equals to V over molar volume. So now we have a reacting mole of 0.33 to give us this. So if 2 reacted with 1, but now we have 0.33 to react to it. So just do a simple cross multiplication. So the number of reacting moles of oxygen will be 1 times 0.33 over 2. So that gives us 0.165 mole of oxygen. So the number of oxygen molecules required now is what we need, but we know the number of moles. Now if you recall that 1 mole of oxygen is equals to Avogadro's number, that is 6.2 times 10 raised to the power 23, which we are given here. We're given Avogadro's number. So 1 mole of oxygen contains this number of molecules. So if we now have 0.165, we have to calculate the number of oxygen molecules required. So 0.165 mole of oxygen would give us 0.165 times 6.023 times 10 raised to the power 23. So we have 9.94 times 10 raised to the power 22 molecules. So this is the amount of oxygen molecules that will be required to react with SO2 gas to give us SO3 gas. Okay, so I have another theory question here for us to solve. This is 3CII of the same exam question. And it says from the equation below, this is the equation, you have calcium carbide plus water to give us calcium hydroxide and ethane gas. So we asked to find the volume of ethane produced at STP from 3.2 grams of calcium carbide. We are given the relative atomic masses, the molar volume at STP. Okay, now this is, we are given a particular equation. This is the equation which I rewrote outside for us. Calcium carbide plus water to give us this. Now we asked to find the volume of ethane produced at STP from 3.2 gram of calcium carbide. We asked to find the volume of ethane produced. So the first thing now is to write out our mole ratios. Now our mole ratios give us 1 mole of calcium carbide react with 2 moles of water to give us 1 mole of this and 1 mole of ethane gas. So this is our mole ratios. Now from our mole ratios, we are told to find the volume of ethane which will be produced from calcium carbide. Now from the mole ratio, we have 1 mole of calcium carbide gives us 1 mole of ethane gas. From this equation, 1 mole of calcium carbide gave us 1 mole of ethane gas. Now, what is the volume now which you'll be expecting from 3.2 gram of calcium carbide? Now you can see the relationship here now. We have to find the volume from mass. So these are mass volume relationships now in stoichiometry. So first we need to find the number of moles of 3.2 gram of calcium carbide. Now first find the RMM, the relative molecular mass of calcium carbide. Now calcium, which is 40 plus 2 into carbon, which is 12. Now this gives us 64 gram per mole. So 1 mole of calcium carbide is 64 gram per mole. Now we are told 3.2 gram of calcium carbide is the one reacting now. So if you recall that N is equals to reacting mass over molar mass, 1 mole is 64 gram. But how many moles now is going to be 3.2 gram from the question? 3.2 gram. So N will be equals to 3.2 gram over 64. So N gives us 0.05 mole. So we've been able to find the number of moles of 3.2 gram of calcium carbide. So it doesn't end there actually. We found the number of moles, right? So that is synonymous to if 1 mole of calcium carbide gave 1 mole of ethane gas, 0.05 mole of calcium carbide should also give what? 0.05 mole of ethane gas. So 0.05 mole of calcium carbide would also give us 0.05 mole of ethane gas. But now don't forget, we are asked to find the volume. It says calculate the volume of ethane produced at STP. So using the relationship now that N is equals to V over molar volume. Now our volume at STP. Now we are told from the question that calculate the volume of ethane produced at STP from this mass. So since 0.005 mole of ethane is what is being produced, and I have to find the volume at STP. It is unknown. And the molar volume at STP is 22.4 dm cube per mole. So on cross multiplying now, the volume of ethane produced will be 0.05 times 22.4. So it's going to give us 1.12 dm cube. So this is the volume of ethane gas which will be produced at STP from 3.2 gram of calcium carbide. Okay, so this is another exam question. We're still solving the same 2019 Eco Pass question. Now I'm solving 6B II. I'm solving questions related to stoichiometry. And it says calculate the mass of copper 2 oxide which will react with a solution containing 3.6 gram of tetraoxosulfate 6 acid. And the first thing to do is to write your chemical equation. It says calculate the mass of copper 2 oxide. This is copper 2 oxide, which will react with a solution containing 3.6 gram of tetraoxosulfate 6 acid. This is tetraoxosulfate 6 acid. So on combination of these two, we're going to have, it's going to give us so we have the mass of, so this is the chemical equation. So copper 2 oxide reacts with tetraoxosulfate 6 acid to give us copper, sulfate, salts, and water. So the mole ratios 1:1 to give us 1:1. So 1 mole of copper 2 oxide reacts with 1 mole of tetraoxosulfate 6 acid to give us 1 mole of copper, sulfate, salts, and 1 mole of water. Now we have to find the mass of copper 2 oxide, which will react with 3.6 gram of this. So yeah, interested with the reactants now. So 1 mole of CuO reacts with 1 mole of H2SO4. Now we are told to find the mass of copper 2 oxide, which will react with 3.6 gram now of H2SO4. So we need to know now the number of moles which 3.6 gram of H2SO4 contains. So using the relationship N equals to M over molar mass. First, we have to find the molar mass of H2SO4. The molar mass of H2SO4, which is the relative molecular mass. And that gives us 2:1 plus the relative atomic mass of sulfur is 32 plus 4:16. Now remember, we are given their relative atomic masses, so we don't need to cram them. So on solving this, we are going to have 98 gram per mole. So N is equals to M over M. So the mass of H2SO4 we are given was 3.6 reacting mass. The molar mass is 98. So this gives us 0.037 mole. So from the mole ratio, 1 mole of copper 2 oxide reacts with 1 mole of H2SO4. But now we are told 3.6 gram of H2SO4 is what is being combined, is what is coming to the reaction now. So to find the number of moles of 3.6 gram, we use this expression, reacting mass over molar mass, to give us this. So that means that 0.37 mole of copper 2 oxide we also react with 0.37 mole of H2SO4. because 1 mole reacts with 1 mole. So if we have 0.37 mole of H2SO4, it will also react with 0.037 mole of copper 2 oxide. So we have to find the mass of copper 2 oxide, which will be reacting with 3.6 gram of H2SO4. Now, since we know already the number of moles of the reacting element, 0.037, so using that same relationship now, but in this case, we need to find the molar mass of copper 2 oxide. So to find the relative molecular mass of copper 2 oxide, now the atomic mass of copper is 64, oxygen is 16, gives us 80 gram per mole. So now because the number of moles is equal to reacting mass over molar mass. So to find the mass of copper 2 oxide, which will react with 3.6 gram of H2SO4, so that gives us N, which is 0.037 multiplied by 80. So that's going to give us 2.96 gram. So 3.6 gram of H2SO4 would react with 2.96 gram of copper 2 oxide. So now I have a WAEC past question now, a WAEC 2019 past question. So this is the objective question. Now it says, if 6.5 gram of magnesium ribbon reacts completely with hydrochloric acid, how many grams of hydrogen gas would be liberated? Now give me the chemical equation and their atomic masses. It says you have magnesium ribbon reacts with hydrochloric acid to give us magnesium chloride and hydrogen gas. And we're asked to find the number of grams of hydrogen gas which will be liberated from this. So rewriting the chemical equation now to find our mole ratio. So 1 mole of magnesium reacts with 2 mole of hydrochloric acid to give us 1 mole of magnesium chloride and 1 mole of hydrogen. So what this implies is that 1 mole of magnesium would give us 1 mole of hydrogen gas. But now we are told 6.5 grams of magnesium is what we're reacting now. So N equals to M over M. So to find the new number of mole now, since we are told 6.5 grams of magnesium. So the reacting mass is 6.5. The molar mass of magnesium we're given from the question as 24.0. 24. So N be equals to 0.27 mole. So initially it was 1 mole to 2 gives us 1 to 1, meaning 1 mole magnesium gave us 1 mole of hydrogen. But we are told 6.5 gram is the reacting mass now. So our number of moles of magnesium is 0.27. So if 1 mole of magnesium gave us 1 mole of hydrogen gas, so 0.27 mole of magnesium will also give us 0.27 mole of hydrogen gas. So that implies that N equals to M over M. So to find the mass now of hydrogen gas that will be liberated, that's N into M. And the number of moles is 0.27. Now multiplied by the molar mass. And the molar mass of hydrogen is... So recall that we are talking about hydrogen gas. The relative atomic mass of hydrogen is 1. So for 2 atoms of hydrogen, that's 2 times 1. So number of moles, 0.27 times molar mass. So this gives us 0.54 gram. So 0.54 gram. So I have objective question, same like past question. It says how many moles of carbon dioxide contains 60 gram of oxygen? Now, this is carbon dioxide. This is 1 mole of carbon dioxide. 1 mole of carbon dioxide gives us 12 plus 2 into 16. The relative molecular mass. That's 44 gram per mole. So we are told how many moles of carbon dioxide contains 16 gram of oxygen. Now, carbon dioxide consists of 12 grams of carbon and 32 grams of oxygen. So we are told how many moles of carbon dioxide contains 16 grams of oxygen. So if you are to have just 16 grams of oxygen, recall that 1 mole of CO2 contains 32 grams of oxygen. So how many mole now of CO2 will contain 16 grams of oxygen? So by simply cross multiplying, x equals to 16 grams times 1 mole over 32 grams. So x will give us 0.50 mole. So answer is 0.50 mole. And question 12 here says stoichiometry is based on the law of what? What's proportion, constant combustion, and conservation? And stoichiometry is based on the law of conservation of mass, which says that energy can neither be created nor destroyed, but can be transformed from one form to another. So in chemical reactions,
I hope the class was interesting. If you have questions, please drop them in the comment section or send us an email. We will love to help you further. See you in the next class.